continued observation of a moving ship in relation to the horizon has long been used to support the contention that the Earth is a huge round ball in space. Let us imagine that we are watching a ship traveling out to sea, with its speed increased 100-fold. We see that it descends below the horizon as it moves upon the curved surface of our globe. Let us ascend to the stratosphere. As we rise, more and more of the Earth's surface becomes visible. If we were projected farther out into space, the curvature of the Earth would become apparent, and we would see that the Earth is not only a sphere, but a rotating sphere. Back on Earth, we find evidence of this rotation in the apparent nightly motion of the stars. If we, in the middle northern latitudes, watch the stars in the north, we see them describing arcs of circles about a point high above the horizon. Turning to the south, we find the stars moving in larger arcs about a center far below the horizon. This apparent motion of the stars is attributed to the Earth's rotation. But to prove that the Earth is turning, we use a Foucault pendulum. High in this dome, a wire cable is attached. Far below, at the other end of the cable, swings a heavy ball. Note that the path of the swinging pendulum is over the line at the edge of the dial. After an hour has passed, we discover that the path has changed considerably. At the end of the second hour, the path of the pendulum has further changed by the same amount. Since there is no force to twist the pendulum, we must conclude that the Earth on which the dial is set is turning. From outer space, the true motion of pendulum and Earth would be apparent, but to an observer on the Earth directly beneath it, the pendulum at the North Pole would appear to change its direction of swing by 360 degrees every 24 hours. It is this turning of the Earth on its axis that gives us the succession of night and day. We shall now present evidence that the Earth revolves about the Sun. At dawn in early autumn, we observe the constellation Leo in the eastern sky. One week later, we notice that the constellation Leo is slightly higher above the horizon at the Sun's appearance. A month later, we find Leo still farther advanced ahead of the Sun, actually about 30 degrees farther. And now, 1 year later, because of this continual advance, we again find Leo at dawn in the same position as during our first observation. Each day of the year, we find the Sun in a slightly different position in respect to the background of stars. These 12 groups of stars, here outlined into figures for identification, are the zodiacal constellations from which have been derived the signs of the zodiac. They form a belt in the sky, so that after 1 year, the Sun is back again at its original position among them. This motion is only apparent and is attributed to the revolution of the Earth about the Sun. We explain this illusion by an arrow drawn from the Earth through the Sun to indicate the earthly observer's line of vision and the Sun's apparent positions during a year. We shall use this motion picture camera mounted on a revolving platform to illustrate the principle of one proof that the Earth revolves. As the camera revolves, it is photographing the three lights at the right, one nearer the camera than the other two. The photographic record of these lights made by the camera shows an apparent motion of the near light, an illusion resulting from the revolving of the camera while photographing. To observers on the Earth during its yearly revolution about the Sun, the near stars have a similar apparent motion in relation to distant stars, definite proof that the Earth revolves. If we observe stars directly over the Earth's orbit, a near star seems to describe an ellipse among the distant stars. This ellipse is an exact counterpart of the Earth's yearly orbit. If we could transport ourselves to this near star and could watch the Earth revolving about the Sun, we would see that its orbit is slightly elliptic. An ellipse is easily drawn with the aid of a string looped about two pins. The Sun is located at one of the fixed points, and the Earth moves along the path of the moving pencil. The Earth, therefore, is not always at the same distance from the Sun. On or about the 3rd of January, it is nearest the Sun, and on or about July 3rd, it is farthest away. And there is also a variation in the Earth's speed. During January, an assumed line between Earth and Sun sweeps over a certain area. During July, this line sweeps an equal area, but travels more slowly. The Earth travels fastest in January, when the line is shortest. Meanwhile, the Earth turns on its axis, and as it travels in its orbit about the Sun, this axis of rotation is inclined always in the same direction in space, but the inclination of this axis changes in relation to the Sun. During summer, the rays of the Sun sweep across the North Pole. The most northerly advance of the Sun, late in June, occurs at the summer solstice. On this day, the Tropic of Cancer is directly below the Sun, and the entire region bounded by the Arctic Circle experiences 24 hours of daylight. 3 months later, in September, the Earth arrives at the autumn equinox. From a side view, the direct rays of the Sun are seen to be striking the equator. Northern and southern hemispheres are receiving the same amount of sunlight, and everywhere, night and day are of equal length. Again, 3 months pass. Late in December, the Earth arrives at the winter solstice. Now the South Pole has its greatest inclination toward the Sun, which, at its most southerly advance, is directly above the Tropic of Capricorn. The area bounded by the Antarctic Circle now experiences 24 hours of daylight, while the North Polar region is in darkness. On or about March 21st, the Earth arrives at the spring equinox. Again, as at the autumn equinox, the Sun is directly over the equator, and day and night everywhere are of equal length. Another 3 months completes the cycle. The inclination of the Earth's axis, together with the motion of the Earth about the Sun, effect a change in the inclination of the Sun's rays and in the duration of daylight. This results in the succession of the seasons, To dwellers in the temperate zones, each season arouses definite mental pictures. Summertime, long days and warm, the full foliage of green things growing. The autumn's golden harvest time, and the first hint of coming frost. Wintertime, the landscape blanketed with snow, a sun that seems unsympathetic and aloof. And finally, returning spring, unfolding its gay panorama of regenerating life.